Okay, these are the lesson 6.1 activities. We're going to take the dot product of W with itself, W dot W. So that would be -3, 1, 0, dotted with -3, 1, 0. We multiply corresponding entries and then add up the results. So we're going to have 9 plus 1 plus 0 is 10. So that's the -3 times the -3, that makes the 9. 1 times 1 makes 1, and 0 times 0 makes 0. Okay, y dot w, that's 1, 2, -1, dotted with -3, 1, 0. And we get -3 plus 2 plus 0 is -1. Y dot w over W dot W. So I've already calculated Y dot W and W dot W. So this is -1 over 10. Then I want to take that -1/10, Y dot W over W dot W, and multiply it times the vector W. So I have -1/10, which I'm just going to write as -0.1 for space reasons. All right, and then dotted, not dotted, times the vector W, -3, 1, 0. So when you multiply a scalar times a vector, you multiply every entry in the vector by the scalar. So we're going to get -0.1 times -3 is +0.3. -0.1 times 1 is -0.1, and -0.1 times 0 is 0. Okay, now I want the length of W. So that is the square root of W dot W. So that would be the square root of 10. A unit vector in the direction of W. So a unit vector is a vector that has a length of 1, and it has to point in the direction of W. So I just need to scale W by its length. I have to scale it down by its length. So we know the length of W is root 10. So I'm going to scale each entry in W by dividing it by root 10. So this is going to be, -3 over root 10, 1 over root 10, and 0 over root 10. Determine if y and w are orthogonal. So you take the dot product of y and w, which we've already done. Y dot w is -1. We did it in part B, which is not 0, implies they are not orthogonal. Find a vector orthogonal to W. So W is -3, 1, 0. So I'm looking for a vector that I can dot it with. -3, 1, 0, dotted with some other vector that would give me 0 as the scalar. So let's see, if I put a 1 here and a 3 here, that would give me -3 plus 3, and then I put a 0. Actually, I can put anything there because I'm going to multiply it by 0. So maybe I'll pick something random, 7. So that gives me 0. So 1, 3, 7 is orthogonal to W. Find the distance from Y to W. So we look at, we subtract the two vectors and then find the length. So we would do the length of Y minus W. Okay, so Y is, scroll up for a minute. 1, 2, -1. Minus -3, 1, 0. And find the length of this. So this becomes, find the length of 1 minus negative 3 is 4. 2 minus 1 is 1, and negative 1 minus 0 is negative 1. Okay, so then the length is the square root of the vector dotted with itself. So this would be the square root of 16 plus 1 plus 1, or square root 18. Number 2, suppose that y is orthogonal to u and v. Show that y is orthogonal to 2u minus 3v. Okay. So we know y dot u is 0. Because that was given. And what was also given is that y is orthogonal to v, which means y dot v is also 0. So I need to show that y dotted with 2u minus 3v is 0. That's how we show two vectors are orthogonal. Okay, so let's do that calculation. Y dotted with 2u minus 3v. So this becomes, I'm going to distribute my y, and I get y dotted with, well, first I'm just going to write that as plus and negative. Okay, then I'm going to distribute. So I'm going to have y dotted with 2u plus y dotted with negative 3v. And then I can move the scalars around with the multiplication. So this is going to be 2 times y dotted with u plus negative 3 times y dotted with v. Okay, and then y dotted with u is 0. That was given, right? We just wrote that up here. So this is 2 times 0 plus negative 3 times y dotted with v, also 0. It was given, and this is 0. So we have shown that they are orthogonal. Okay, find a set of 3 non-zero vectors in R3 that are mutually orthogonal. Any pair of them is orthogonal. Okay, so I need 3 vectors. I can't use 0, 0, 0 because they said non-zero vectors. That any 2 dotted together are going to give me 0. All right, so let's see. Let's start with 2 vectors that, we'll just pick 2 vectors that are orthogonal. So let's see, I'm going to pick like 1, 2, 3 as my first vector. And now my second vector, I'm going to build to be orthogonal to that. So let's see, I can use 0 entries. I just can't have all the entries be 0. So maybe an easy one would be like 2 and negative 1, because then I would get 2 plus negative 2. That would give me 0, and then I'll put a 0 here. All right, so now my third vector, I have to choose it so that it's orthogonal to both of these. So let's see. I could put 0 and 0 in the first 2 entries. As long as I don't make them all zeros, this is legal. And then maybe I'll put, actually, that's not going to work because of the 3. I could make this 0. And then I can put anything I want in this third entry, 5. Yeah, let's make sure these are all orthogonal to each other. So if I dot these 2, I get 2 plus negative 2 plus 0 is 0. If I dot these 2, I get 0 plus 0 plus 0 is 0. And if I dot the first and the third, 1, 2, 0, and 0, 0, 5, I get 0, 0, 0. Okay, that works. If you dot any two of these together, you get 0. Okay, last one. Two vectors, u and v, are geometrically perpendicular if and only if the distance from u to v is the same as the distance from u to the opposite of v. Okay, so this is the same as requiring the squares of the distances to be the same, which will make our lives a little bit easier because we won't have to do square roots. All right, so we want to find an expression for the distance from u to v squared. Okay, so the distance from u to v, that is okay, so that is the length of u minus v squared. And the length of u minus v, the way you calculate that is you do the square root of u minus v dotted with u minus v. And then we're going to square it. So then the square root and the squaring cancel, and you just get u minus v dotted with u minus v. Okay, and then we can multiply this like the way you would with, say, FOIL. And just remember that these are all vectors. Okay, so we have u dot u minus u dot v minus v dot u, and it's commutative, so this is minus 2 u dot v, and then plus v dot v. Or is it minus v dot v? Okay, yeah. Negative v dotted with negative v is positive v dot v. Okay, so there's my expression for the distance from u to v. Now we want to find an expression for the distance from u to the opposite of v. So this is going to be really similar to what we did above. It's going to be the length of u minus the opposite of v squared, which is, that's actually plus. So this is going to be u plus v dotted with u plus v, which is u dot u plus 2 u dot v plus v dot v. Now we're supposed to set these two expressions equal to each other. So u dot u minus 2 u dot v plus v dot v equals u dot u plus 2 u dot v plus v dot v. Okay, so I can, the u dot u's appear on both sides, so like you can subtract them out. Same with the v dot v's. And so it has to be that negative 2 u dot v equals positive 2 u dot v. So it has to be that negative 2 u dot v equals 2 u dot v, which only happens if u dot v is 0. Which means u and v are orthogonal. So what we did was you just did a little proof, right? We said, okay, if the distance from u to v and u to the opposite of v are the same, that is enough to prove that u and v are orthogonal.